So what if I told you that just by looking at something, you could literally change what it is? I know, it sounds like something out of a sci-fi movie, right? But it's actually a fundamental rule of our universe. See, down at the tiny quantum level, the act of observation, well, it isn't passive at all, it's a disruptive force. Let's dig into why that is.
And that really brings us to the core question of this whole explainer. Can you really look at something without changing it? Now, you're probably thinking, of course I can, but, as we're about to see, the answer is, well, it's anything but obvious.
In a way, the answer is always no. I mean, think about it. Any measurement, any experiment requires some kind of interaction. A thermometer has to absorb a tiny bit of heat from the water it's measuring, right? A camera only works because photons of light bounce off an object and into the lens. So yeah, every observation is technically invasive. But here's the thing. In our everyday world, that invasion can be so gentle that it's practically meaningless. At the quantum level, though, whoa, there is no such thing as a gentle look.
Okay, so let's start in the world we all know and love, the classical world. Think baseballs, planets, all the stuff that operates on predictable, familiar rules. So in this classical world, we can make our measurements almost perfectly gentle. Let's say you want to see which way an arrow is pointing. You could bounce a single photon of light off it. And if you think that's too much, you can use an even weaker particle. The point is, you can dial down the intrusiveness until the effect on that arrow is basically zero. The measurement is, for all intents and purposes, non-disruptive.
But the moment we shrink down to the realm of atoms and electrons, all those nice gentle rules get thrown right out the window. This is where we run headfirst into the famous, and let's be honest, often misunderstood, quantum observer effect.
And this is really the heart of the difference. In the classical world, measurement can be as gentle and non-invasive as you want. But in the quantum world, nope. Any interaction strong enough to actually measure a quantum system is also, by necessity, strong enough to fundamentally disrupt it. It's like trying to find out where a soap bubble is by poking it with your finger. You can't just look without serious consequences.
So how does this disruption actually work in practice? Well, let's take a look at a super weird property of particles like electrons, called spin. Now, it's not literally spinning like a top, but it acts as if it has this tiny internal magnet. And for our purposes, that magnet can only point in specific directions. Let's just call it up or down along any given axis we choose to measure.
Okay, let's walk through a classic experiment here. First, step 1. We measure an electron's spin on the vertical axis. Let's call it the z-axis. And let's say we find out it's up. Okay, simple enough. Now, for step 2, we change things up. We measure its spin on the horizontal, or x-axis. We get a result, but honestly, we don't even care what it is. The really important part is step 3. We go back and measure the spin on that original vertical axis again. Now, we already know it was up, right? So, what do you think we're going to find?
It's gone. The original result is completely gone. Our new measurement on that same vertical axis is now totally random. It's a coin flip, a 50-50 chance of being up or down. That second measurement, the one we did on the horizontal axis, it didn't just look at the electron, it completely scrambled the information about its original vertical spin. Just wiped it clean.
And that is the crucial takeaway right here. The act of measuring one component of the spin destroys the information about another component. And listen, this isn't because our tools aren't good enough. It's not a technology problem. It's like the universe itself has a rule that says you're just not allowed to know both at the same time. To know the X spin is to fundamentally forget the Z spin.
So why? Why is this happening? To even begin to understand this, we have to wrap our heads around the idea that the classical world and the quantum world seem to run on two entirely different operating systems, two different kinds of logic.
Now, the operating system for our everyday world, the one we're all familiar with, is called Boolean logic. This is the logic we use all day, every day, without even thinking about it. A statement is either true or it's false. A light is on or it's off. There are no fuzzy in-betweens. Simple, right?
A perfect example of this is a simple six-sided die. Before you roll it, you know there are exactly 6 possible states it can land on. The set of possibilities is totally clear and fixed. It's going to be a 1, or a 2, or a 3, and so on.
So using this Boolean logic, we can ask questions about the die. Like, is the result odd? Okay, that refers to the set of states 1, 3, 5. Or is it a number less than 4? That's 1, 2, 3. We can combine these with and or. But here's the absolute key. Asking one of these questions doesn't mess up the answer to another one. Checking if the result is odd has zero effects on whether or not it's less than 4. The propositions just don't interfere with each other.
And that is the complete opposite of what happened in our electron spin experiment.
And this brings us right back to that stark contrast at the very heart of modern physics. It really seems like we're living in two completely different realities all at once.
First, there's the classical world, the world of our senses, of dice and arrows. It's governed by these clean, predictable rules of Boolean logic, where things have definite states, and just looking at them doesn't fundamentally rewrite their properties.
And then underneath all of that is the quantum world, this bizarre, counterintuitive reality of electron spins that plays by a completely different, disruptive set of rules, a world where every observation is an act of both creation and destruction, where finding one answer actively erases another.
And so we're left with this really profound question. Our entire civilization, everything, is built on Boolean logic, from our computers to our legal systems. But if the fundamental particles that make up our world, if they don't obey that logic, then what logic do they obey? And what does that imply about the true nature of reality itself?
All right, welcome. Today we are diving head first into one of the most fundamental and, let's be honest, one of the just weirdest parts of reality, quantum logic. We're going to explore a world where the very rules of truth that you rely on, that I rely on every single day, well, they just kind of fall apart. So let's start with a question that, honestly, sounds a little ridiculous. Is the statement A or B always the same as B or A? You know, if I ask, is the sky blue or is the grass green? Is that any different from asking, is the grass green or is the sky blue? I mean, of course it's the same, right? Well, in the quantum world, the obvious answer is almost never the right one. Okay, so before we break the rules, let's, establish what they are in our normal, everyday world. This is classical logic. It's the bedrock of everything from the computer in front of you to how you win an argument. It's what we live by. It's stable. It just makes sense. All right, to put this to the test, we're going to use two super simple statements about a particle spin. Just picture a tiny, tiny spinning top. So proposition A is about its spin on the vertical axis. You could call it the up-down spin, or z-spin. And proposition B is about its spin on the horizontal axis, the side-to-side spin, or x-spin. That's it. Just two things we want to know. Okay, here's the absolute #1 rule of classical logic, the thing that makes it all work. Observation is gentle. Looking at something doesn't change it. You know, if I look for my keys on the table and then I check for my wallet, looking for the keys doesn't magically make my wallet vanish. The order? Totally irrelevant. So let's do a quick test in our normal classical world just to prove what we all feel in our gut. We're going to see if A or B is true. Okay, so the procedure is pretty straightforward. You can see it right here. First, step 1, we gently measure that z-spin. If we get a +1, awesome. A is true, so A or B is true, we're done. If not, no big deal, we move to step 2 and gently measure the x-spin. If that's +1, B is true, so A or B is true. Super simple, totally logical, right? All right, now let's just flip it around and test B or A. We'll measure the x-spin first, then the z-spin. And since our measurements are, gentle, they don't mess with anything, the final answer is, well, it's exactly the same. We get the same truth value no matter which way we go. And right there, that's it. That's the foundation of how we think the world works. In classical physics, A or B is identical to B or A. The order doesn't matter one bit. Hold on to that thought, because now we're going to completely shatter it. Okay, let's jump into the quantum realm. Same experiment, but here's the twist. The act of looking is not gentle. Here, a measurement isn't just a passive look. It's an interaction. It fundamentally changes the thing you're looking at. All right, to really nail this down, let's set up a special case. Let's say we have a little inside info. We know for an absolute fact that a particle has been prepared with its z-spin as +1. So proposition A is true right from the get-go. It's a given. Okay, time to run the tests. First, on the left, we test A or B. We measure z-spin first, and since we already know it's +1, guess what? We get +1 every single time. Boom, the statement is true. We don't even have to bother checking B. But now, look at the right. What happens when we test B or A and measure that x-spin first? And this is the whole mind-bending part right here. The moment we measure the x-spin, we force the particle into a definite horizontal state. And in doing so, we have completely destroyed its original z-spin state. The simple act of asking about B has completely changed the answer to A forever. And the fallout from this? It's just staggering. By measuring the x-spin, we've randomized the z-spin. So now, when we go to check it, there's a 50% chance it's negative. And because there's a 50% chance the first x-spin measurement was also negative, that means there's a 1 in 4 chance, a 25% probability, that we find the whole thing is false. Think about that. We started with a statement that we knew was true, and now there's a 25% chance it's false, just because we asked the question in a different order. So yeah, this isn't just some little quantum quirk. This is a fundamental breakdown of the logic we thought was unbreakable. This shakes the absolute foundations of what we think of as truth and reality. So let's just lay it all out, side by side. In the classical world, your path doesn't matter, you always arrive at the same truth. But in the quantum world, your path changes the destination. The truth literally depends on the order you ask the questions in. Wow. And just when you think it can't possibly get any weirder, it does. What happens if we try to ask about A and B? What if we want to know if they're both true at the exact same time? Well, that's where the question itself starts to break down. Well, to get why that's a problem, you have to understand a really basic idea in science: verifiability. Basically, for something to be true, you've got to be able to check it, and then check it again, just to be sure, and get the same answer both times. And that's exactly where this whole thing falls apart. Okay, so let's say we measure z-spin. We get +1, great. Then we measure x-spin. We get +1, awesome. We might think, A and B is true. But here's the catch. If we try to go back and double-check that z-spin, we can't. Our measurement of the x-spin scrambled it. So the statement A and B are true isn't actually false. It's worse. It's unverifiable. You can never truly prove it. You know, what we've been digging into here, this isn't some obscure little detail. This is actually one of the most famous laws of the universe, just in disguise. This is a direct consequence of Heisenberg's uncertainty principle. And this isn't just some weird thing with spin either. It applies to other pairs of properties, like the really famous one, position and momentum. It's like a cosmic seesaw. The more precisely you nail down one of them, say a particle's position, the more the other one, its momentum, flies up into the air. You simply cannot know both perfectly at the same time. And all of this leads to a conclusion that is it's just wild. In quantum mechanics, asking a question like, what is this particle's exact position and its exact momentum, isn't just a wrong question. According to the physics, it is completely meaningless. It's not wrong. It's not even wrong. The question itself is broken. The universe literally doesn't have a way to answer it. And that just has to leave you with this one final, really big thought. I mean, think about it. Our brains are built for our world, for rocks and trees and, well, classical logic. But the fundamental fabric of the universe, it's playing by a completely different rulebook. So it makes you wonder, right? What other truths about reality are hidden from us, simply because our logic, our brains, aren't even equipped to form the right questions?